This is the SVLM user interface. From here, we can perform all of these 6 security verification tasks through conversation. Let's first try the security verification check. We can start uh, chat by through a query to list all frameworks that use fuzzing techniques for verification of hardware design. The response what we got from the SV-LLM. It talks about different frameworks like RFuzz, GraphFuzz, ResFuzz, and so on. And also it gives a list of references. If we look at these words very carefully, then we will find these frameworks actually exist in the literature and they are very well known. And also we can go to these papers for using these references. So this response is accurate, factually grounded, and aligned to the query that we put to the SQL. Now we ask the same question to the ChatGPT-4 and here is what it generated. If we look at the response that it mentioned about few frameworks like Dagger, WhistleFuzz, CFuzz, FastSD, which are actually fabricated. They don't exist in the literature. So ChatGPT 4o has synthesized these names, randomly combining relevant sounding uh, concepts to create these fictitious tools. Talked about VFuzz and SimFuzz, which actually a software verification fuzzing techniques, and also it talks about RFuzz, which is correct, but the information it has given regarding the RFuzz, like the publication venue, author names, and the link, these are actually fully incorrect. Let's ask SVLM whether it can help us to identify security assets in an SoC design. When we write this the SV-LLM identify the intent of this task. For doing this, it needs two specific information. One is the path of the design specification and another is the path for the code. This we will work with newer V32 design, which is a RISC-V based SoC design. Let's submit the query. Since this is a SoC design, it will take some time to process the query and return the full SoC security assets. It took around 20 minutes to generate all these assets. So this is a long list of security assets generated by the SVLM. Um, and if there is a JSON file also down which we can download. And if we look at each of these assets, they are accompanied with the functionality, the security objective, and the justification. The justification actually explains why SVLLM considers this as a security asset. I shall walk you through the threat modeling and test plan generation agent in SVLLM. We can try this with a query like help me generate security test plan for SoC design. After submitting this query, as we can see, SVLLM is asking for the asset list in a JSON structure. Since we have already generated this list of assets in the previous step, so the security asset identification agent, we can simply upload that file here. After submitting this list of assets, SVLLM agent launches into a two-phase interactive process. What is the technology node and the foundry being used for manufacturing? There are more questions like this about the cryptographic keys and about the uh, design flow, the supply chain. All this help the agent understand the threat models. For example, if the chip is manufactured at an untrusted foundry or uses an older node, it might be more vulnerable to fault injections or overproduction attacks. After answering these questions, the agent moves to the questions about planning, the verification strategy, and testing capability. Now the questions shift to more practical considerations, like will you verify at the RTL level, netlist, or the board? Do you have formal or emulation platforms available? Which tool chain you are going to use? What is the size of your team? How much time and budget you dedicated to security verification? This question help uh, to tailor the test plan to fit to the verification engineer's project constraint, balancing the thoroughness with feasibility. After taking all the information, SVLM starts processing and uh, identify the threads. Here we can see the output of the task. As you can see, four relevant threads are identified and total 12 test plans have been generated. And if we look one of these test plans, like there is a test plan on uh, you can see this test plan checks whether the L bit in npm entry correctly logs the configuration, preventing any unauthorized access or privilege escalation. It combines formal simulation, hardware-software co-verification, and gate-level testing to ensure the behavior holds from RTL to gate level. And also, we can see that it considers all the input from the uh, user, like it considers all the cadence toolchain here, as user has mentioned about the cadence toolchain. So this is one of the output, and
another key agent in the SV-LLM framework is the bug detection agent. Now, let's take a look at how this agent works in practice. Now, we are giving a prompt to our SV-LLM framework, and we are asking it to help us detect the security vulnerability in the design. Now, as we haven't provided any RTL design in the as an input, it is asking us to provide an RTL design. We can also provide the RTL design as part of the prompt, and let's upload the design. So within this time, let's talk about the design. So this design pass verification is a simple RTL module that performs hash-based authentication. It takes two 8-bit hash inputs, input hash and correct hash, and compares them with a validation signal is hash valid. When this signal is asserted, if the hashes match, the authentication flag is set high, otherwise it's cleared. This module also drives a next state output based on whether the hash was valid. However, there is a logical flaw in the state transition behavior. Regardless of whether authentication succeeds or fails, the module always transitions to wait state as long as is hash valid is true. This means that even when the input hash is incorrect, the system proceeds to the next state instead of staying in the correct state or triggering a retry mechanism. Now, let's find out if SV-LLM can catch the exact bug or not. As we can see in the response provided by SV-LLM, uh, it says in this modified Verilog code, FSM is implemented to verify the authenticity of hash values. Then it describes the um, work process of this FSM. And finally, it says that if the hashes do not match, the authentication flag remains false, signaling an unsuccessful authentication attempt. After the authentication process, the system enters to wait state where it waits for further instructions before proceeding with another authentication operation. Then finally, it also says, for instance, an attacker could manipulate the hash input to trigger a state transition to the wait state even when the authentication fails. This could lead to unauthorized access or other malicious activities, highlighting the importance of thoroughly validating all state transitions and outcomes in security critical systems. Now, as we can see that SVLLM can perfectly detect the bug where the vulnerability is placed in this design, and also it tells us how to exploit this vulnerability.
This was the RTL which was used in our bug detection framework, and there is a perfect error, a critical bug here. Even if the authentication fails, the system transition to wait set, allowing a bypass without valid credentials. This is a classic security flaw. And in our SV-LLM app, when we are giving the query, it is asking us to give the bug explanation file and the RTL design, where it can help us to create a test bench to validate the security bug in our design. So behind the scenes, the framework creates a test case scenario, constructs a system verilog test bench, checks for syntax error, and ensures simulation success. As it is using model sim, so the LLM use the feedback from the model sim, so it generates that kind of test bench which are perfectly simulatable and syntax error free. So here is the generated test bench. It features clock generation, reset logic, and precise input stimuli aligned with the described bug. And the test bench reflects the test stimuli perfectly, and you can always download the code from here. And the simulation output always have a strobe monitoring, so you can see the signals value at the all possible time scales. And after downloading the code, you can see that the bug is perfectly reflected, where the input hash and the correct hash doesn't match. It triggers the bug, and it goes to wait state despite a failed authentication. This is the bug where this stimuli is perfectly reflected in our generated test bench, and it uses the strobe monitoring, and where you can see the value of all of the signals at each timestamp. So this is the bug validation framework by using.
Hello everyone. I will introduce the security property and assertion generation agent within our SV-LLM framework. Here we are typing that, can you help me in generating security property for my design? We can see that the SV-LLM framework can detect that we are talking about security property generation agent, and it is asking me to provide a design because I didn't initially give any design. Now we can also put the design in the prompt, or we can also choose a file for providing the design. Here I am giving a design that is a FIFO design. To demonstrate the example, the design file implements a parameterizable buffer with write pointer, read pointer, and a counter that tracks occupancy. On each clock, a valid write request enqueues data when full is low, while a valid read request dequeues data when empty is low. A synchronous reset initializes all pointers and the counter to 0. Here we can see that after providing the input design, it actually provides us a totally executable system verilog assertion or SVA file that we can also download, and we can also look at the properties, scenarios, natural language properties, and executable system verilog assertion. Now, let us ask SV-LLM about one of the generated properties and find out what it elaborates about this property. So now we are giving the query, please elaborate the second property from the generated list. Here you can see that this property talks about that the FIFO FSM may not handle the reset condition correctly, potentially leaving the system in an undefined state. And when we asked about this property to elaborate this, we found out that it is providing a scenario, the conditions for fulfilling this property, the specification for the property, and also the purpose. So the purpose of this property is it ensures all pointers and counters are reset to their initial values, thereby preventing any residual data or state from affecting subsequent operations.